Hello, this is Math Jazz from Almost Cool, and today we are continuing to review for the final that my students are taking taking in a few days. So, we have some questions here that we'll go through for about an hour, and then tomorrow we will pick up where we leave off, continue doing more questions. I'm going to try and do 2 sessions, one in the morning tomorrow and one in the evening tomorrow. But that said, let us get into these problems. We want to find the absolute minimum for f on this closed interval. So we have f of x equals x squared minus 4 over x squared plus 4 on the interval -4 to 3. So here's our function and our interval, and we want to figure out what the maximum and minimum values are. Now this is a multiple choice question, so really I'd just plug in all the points and find the biggest one, and that's your max. But if this were a free response question, then you'd take a derivative. So we go f prime of x equals, we're going to use we could use logarithmic differentiation, or we could use the quotient rule. I'm going to use the quotient rule, so that's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. And we're going to set this equal to 0. We also want to find any asymptotes, or any, points of discontinuity. Those are also critical points. However, looking at our denominator here, this denominator has no zeros, so this function here is not going to have any asymptotes. So we won't have to worry about that for this particular problem. But we will need to find zeros of the numerator. We won't need to worry about any zeros of the denominator, so we're just going to throw that away, set the numerator equal to 0. This is actually equivalent to, we're just multiplying by the denominator on both sides, so the denominator will cancel from the left, and 0 times the denominator is still 0 on the right. So what we end up getting is x squared plus 4 times 2x minus x squared minus 4 times 2x equals 0. And like I said, this is just what we'd get if we'd multiply by this on each side of this equals sign. We'd get the denominator to cancel on the left, leaving us with this. And we get 0 times x squared plus 4 squared, which equals 0 on this side. So anyway, we get this. And now we have to figure out what the roots of this thing are. So we have to multiply everything out. We get 2x cubed plus 8x minus 8x cubed. Sorry, not 8x cubed. 2x cubed plus 8x equals 0. This term will cancel with that term, and it leaves 16x equals 0, or x equals 0, as our critical point. So now the maximum, by the extreme value theorem, we know there is a maximum. And by Fermat's theorem, we know that the maximum is either at the end points of the interval or at the critical point. So we're going to plug in our endpoints, -4, 3, and 0, into our function. The biggest of these is the maximum. The smallest of these is the minimum. Okay, so let us do that. We get f of, let's do -4 first, equals, is that off screen? That's okay, we can scroll down. F of -4 is equal to -4 squared plus 4 times 2. Sorry, I am plugging this into the derivative. I mean to plug this into the function, which I can't see because it's off screen. Okay. So that's going to be negative 4 squared plus, right, minus 4 on the top, and negative 4 squared plus 4 on the bottom. So that's 16 minus 4 is 12 on the top, and 16 plus 4 is 20 on the bottom. Cancel out a 4, we get 3/5. That's the value at negative 4. Now we'll plug in 0, because that's our critical point. So that's going to be 0 minus 4 over 0 plus 4, which is equal to negative 1. And then we're going to plug in 3. Because that's the other end of our interval. Yes, that is the other end of our interval. F of 3 equals 3 squared minus 4 over 3 squared plus 4, which is equal to 9 minus 4 is 5 on the top, and 9 plus 4 is 13 on the bottom. Now the biggest of these three numbers is our maximum. And let's see. This one's about 0.6. Well, this one is exactly 0.6. This one here, that's a little bit more than 0.3, but it's not. Oh, well, okay. So this is actually easy, because this is going to be smaller than a half, because 6 over 12 is a half. 5 over 12 is less than a half, and 5 over 13 is less than that. So this is less than a half. This one is bigger than a half, so this is the biggest of these three numbers, because positive numbers are bigger than negative numbers, and this is bigger than a half, that's less than a half, so this is our max. We were asked for the minimum value on the question. Look, it says so right there, minimum value. Okay, so we're actually looking for this one. That's the only negative value, so it's the smallest one. So this is our absolute minimum. Okay, so looking back at our next problem, let us scroll down to center that. For what value of c is the function g continuous? Okay, so this is not such a hard question. It's a little bit maybe tricky for some students to figure out exactly what it's asking. It says, what value of c is the function below continuous? The way that we're going to do this is we're going to plug in 2 for x, since that's the point where we're splitting. So I'm going to write my function here, f of x equal, g of x. Not that it matters. We can call it f, we can call it g, as long as we're consistent. G of x equals this piecewise function defined by cx squared minus 4c over x minus 2 when x is less than 2, and cx plus 1 when x is greater than or equal to 2. So here is our function. We notice that we are splitting at 2. Now, what we're actually doing, the whole process is, this chunk is continuous because it is a rational function. This chunk here is continuous because it's a polynomial, so the limits for each of these functions are equal to the values of each of these functions. To be continuous, we need to have the function's value, g's value, equal to the limit from the right and equal to the limit from the left. So what we need is the limit of the left chunk to equal the limit from the right chunk, which is also equal to the value of the function, which is going to be when we plug 2 into this. So there's a little bit of fine detail that's going on here, but basically this chunk is continuous, so its value equals its limit. This chunk is continuous, so its value equals its limit. And so what we're doing is we're just setting the value of this equal to the value of this at 2. So if that went fast for you, like the reasoning for it, when you see one of these problems, all you do is you set the two parts equal to each other, plug in the splitting point. In this case, 2 is our splitting point. So we get c times 2 squared, so that we get 4c minus 4c over, oh, that's unique. Okay, so we're going to need to factor the top, actually, before we do anything. So we're going to factor the top. We get c times x minus 2 times x plus 2 over x minus 2. And those will cancel. Now we're going to set that equal to the bottom part, which is cx plus 1. This will get rid of all the problem issues that we had. We had a 0 over 0 indeterminate form. So now we get cx plus 2c equals cx plus 1. You know, after we cancel this out, we distribute the c times x plus c times 2. That's this side. The other side is unchanged. Now we're going to solve for c. Oh, we can also plug in 2 now that we've canceled out the offending term here, the x minus 2. So we get 2c plus 2c equals 2c plus 1, or we could have just canceled the c's, and that would work the same. We're going to subtract 2c from both sides, so we get 2c equals 1, which gives us c equals 1/2. This is the value that makes this continuous. Now, it's possible to set up this type of a problem where you get multiple values of c that are continuous, and you might be asked that, say, for which values of c is this continuous, but in that case you'll get something like a quadratic, and you'll just use the quadratic formula to find the 2 roots of your quadratic for c. But this is not a very hard problem. We had a little problem because of an indeterminate form at x equals 2, but we were able to cancel out the offending terms and solve, so that's not so bad. Okay, so we want to look at our next problem. So our next problem is going to be the derivative of this integral. So we're using the second part of the fundamental theorem of calculus for this, which is maybe the scarier part, I think. I think if people were asked like which part of the fundamental theorem of calculus looks scarier to them, it's probably the second part. Anyway, we have the derivative d dx of the integral from 3 to x squared of natural log of t minus 1 dt. So this is the function that we're taking the derivative of, and it's not so bad. The fundamental theorem of calculus says that we can just take this function, plug it in for t in this function, and then multiply by the derivative of that. And the way that we do that is through the chain rule, and you know, in class I would explain all of the steps for how this works, but we're just going to get the answer. X squared minus 1 times 2x. Well, what happens if this function, or this limit here, is a function instead of a constant? Say, for example, let's redo this with 3x in the lower limit. Well, the top part happens exactly the same as we did it before. We get this. But now we're going to subtract, because with bottom limits we subtract. We're going to go ln 3x minus 1 times the derivative of 3x, which is 3. This is how the new problem would work. So that's not so bad either. So what happens is you plug the top limit in to your function in place of this variable, and you multiply by the derivative of that. Then you subtract what you get when you plug this in to that function in the same places, and you multiply by the derivative of that, which in this case is a constant. Derivative of a constant is 0. That's why we killed off the second term, the negative term, in this case. But that might not happen on the exam. On the exam, it's totally fair to have a function as the top limit and a function as the bottom limit. So don't be scared if that happens. It's totally easy to handle it. So let's look at our next problem. We want to use linear approximation to approximate the hyperbolic sine of 0.1. So here's the thing. We no longer do hyperbolic sine in this class. A little bit sad. I think that it's an interesting function. It actually has some neat applications in engineering. But we don't do it, so we're going to alter this question to approximate sine of 0.1, which is more likely to show up on your exam. So here's our function, or our value, sine of 0.1. We're going to do linear approximation. So what we want to do is we want to find a value of x that's easy to take the sine of, that's also close to 0.1. So x equals 0 is probably a good pick. That's pretty close to 0.1. I guess x equals pi over 6 might be good. The pi is about 3. Pi over 6 is about a half. I guess 0 is closer to 0.1 than pi over 6, because this is a little bit bigger than a half. So a little bit bigger than 0.5 here. 0 is a better choice, so we're going to use that. But it's something that you'll want to check, you know, just what is the actual best point to guess. So 0 is where we're going to approximate. We're going to find the tangent line at 0, just like we did early in the semester. We didn't call it linearization then, but that's what we're doing, is just finding a tangent line at 0. So we take f of x equals sine x. We take a derivative, f prime of x equals cosine x. And then we plug in 0. So sine of 0 equals 0. Cosine of 0 equals 1. This is our point. This is our slope. This gives us a line. Y minus the y coordinate equals the slope times x minus the x coordinate. So the point 0, 0 is our point, because x equals 0 and y equals 0. When we solve, y equals x is our approximating curve. So that means that when we plug in x equals 0.1, we get y equals 0.1 as well. We plug into there. This is our approximation. There is someone waiting at my door. Forgive me, I'll take just a second to answer. Okay, so I am back. Okay, so our next problem is going to be, we're going to find the, is that the nth derivative? No, that's the second derivative of our function. So let us find our second derivative. We have s of t equals t to the 1/3 plus t to the 2/3. So the first derivative is going to be 1/3 t to the negative 2/3 plus 2/3 t to the negative 1/3. And then our second derivative is going to equal negative 2 over 9 t to the negative 5 over 3 plus 2, sorry, over, that's not going to be plus, that's going to be minus 2 over 9 times t to the negative 4 over 3. That is our second derivative. So that was just the power rule twice. That's not so bad. Oh, but we weren't asked, if you notice, we weren't asked to find the second derivative. We were asked to find the second derivative's value at t equals 1. So s double prime of 1 equals negative 2/9 times 1 minus 2/9 times 1, which is negative 4/9. Okay. And that does appear to be one of the options available, so I guess I can still do the power rule. Anyway, next problem. We want to find all vertical asymptotes of this function. So, let me write down the function. We have y equals 3x minus 2 times x plus 1 times natural log of x plus 5 over x plus 4 times x minus 2. The nice thing here is it's completely factored. So we know that the x minus 2 terms are not going to produce asymptotes. We know that x minus 4 will be, x plus 4, so gives us that x equals negative 4 is a vertical asymptote. But we also know that the natural log of x has an asymptote at 0, so when we add 5 inside the function, that translates to the left 5, so this will give us an asymptote at x equals negative 5. So we have two asymptotes, two vertical asymptotes, one at negative 4, the other at negative 5. I think we also have, if we were looking for one, a horizontal asymptote, but we were not asked to find that, so I'm not going to bother. So I think that those are our two asymptotes. That wasn't so hard to find. This is almost a rational function. Let's take a look at our next problem. Our next problem is, for the definition of limit, find the largest value of delta that corresponds to epsilon equaling 0.06. So this is a type of problem that I don't see come up very often on exams anymore. I don't think that we really do a lot of epsilon delta stuff on the final, which is a shame because epsilon delta proofs are amazing. They're really like, I mean, they're the foundation of everything. So they're like, that's a big indication of their importance for calculus. Everything in calculus depends on them. But the other thing about epsilon delta proofs is that they're kind of the best introduction, I guess, to what a professional mathematician actually does in calculus, in that you have these abstract problems that you have to come up with creative ways to approach these problems and find solutions to them. And I think that the maturity that you get from doing epsilon delta proofs in mathematics, the mathematical maturity you get is beneficial. Anyway, so we want the limit as x goes to 2 of 3x to equal 6. We want to use an epsilon of 0.06. We want to find the largest delta for this epsilon value. Okay, so the shortcut to all of this is that since this is a line, the delta that we get, or the delta that we want, is always going to be the epsilon divided by the absolute value of the slope of the line. So that'll give us a delta of, here's epsilon over the absolute value of the slope. Slope is 3, so absolute value 3 is just 3. It gives us 0.02 as our delta. That's the simple, fast way to do this type of problem. And if this were in the middle of the course, we would actually maybe do the epsilon delta proof. But I don't think that that's likely to show up on the exam. And we're at the end of the semester, so if you're interested in epsilon delta proofs, I have a series of epsilon delta proof videos on this channel. You can go watch them. And if you're one of my students, do that after the final. Okay, that's my tip for you guys today. Okay, so let's look at the next problem. The next problem says a certain isotope has a half-life of 40 years. This is an exponential decay question, so we don't do those in this class anymore, so we will skip question 8 in the document. Okay, so the next question is, a rectangular box with a square base is to hold 4,000 4,000 cubic centimeters. Okay, so we know that the volume equals 4,000. We know this is a box. The materials for the sides of the box cost 2 cents per square centimeter. I'll draw a box here. Okay, so we have a box. We know that we have 2 cents per square centimeter for the side and 1 cent per square centimeter for the top and bottom. So 2 cents for the side, 1 cent for the top and bottom. Okay, and what do we know? We know it is a square base, so this side is x. This side is also x, this side is y. So that means that our cost function as a function of x and y is equal to, so the top and bottom are going to be x squared plus x squared. So we get 2x squared times 1 cent. And then the sides are going to be, each side is y tall by x wide. So we get, and there are 4 of them, so there are 4 times 2 times xy. This gives us the cost of our box. Okay, so, but this also is a 2-variable function. This is a single variable calculus class, so there's got to be a way to collapse out one of these variables. So what we know is the volume is equal to the length times the width times the height. This here gives us an equation that relates y to x, so we know that y is equal to 4,000 over x squared. We plug this into the cost equation, getting our, this is an arrow by the way, we get our cost function is going to be c of x equals 2x squared plus 8x times 4,000 over x squared. We're going to cancel out the square immediately with the x up there. So we get 2x squared plus 32,000 over x. Now, I didn't actually read the full question, but this is probably, let's see. It says, part A, if the base has side x, express the cost of C. Cost C of the box as a function of x. Okay, so this is part A of the question. Part B is find the dimensions of the most economical box. By economical, they mean, of course, box of least cost. So we want to minimize this. So we're going to find the derivative. C prime of x equals 4x minus 32,000 over x squared. Set that equal to 0 to find the critical points. So that means that 4x squared equals 4x squared equals not squared at all. 4x equals 32,000 over x squared, which gives us, cancel out a 4 here and here, we get 8,000. So x cubed equals 8,000. So that gives us x is equal to 20. Y is going to equal, well, we know that y is equal to 4,000 over x squared. So that's 4,000 over 20 squared, which is equal to 4,000 over 400, which is equal to 10. Y equals 10. Those are the dimensions of our box. And, okay, so we didn't prove that this is the minimum cost. We know this is a critical value. We didn't prove it's a minimum. How do we prove it's a minimum? Well, there are 2 ways. The first derivative test or the second derivative test. We're going to use the second derivative test. Just because this derivative that we have here, c prime, it looks really easy to take a second derivative of. That's the drop. So the pros and cons of the 2 tests are, first derivative test means you don't have to take a derivative, but you have to plug in 2 points. And you have to make sure that those points are close enough to the critical point that you're not getting the wrong signs. So those are the pros and cons of first derivative test. Second derivative test, the pro is that you only have to plug in one value and you don't have to worry about, did I pick things that are close enough? But the drawback is you have to take a derivative, and that's sometimes difficult. This derivative looks easy to take, so we're going to use a second derivative test. So we get c double prime of x equals 4 plus 2 times 32,000 is 64,000 over x cubed. Hey, look, this is a positive number. The numerator is a positive number. The denominator is a positive number when we plug in 20. Positive plus positive equals positive. Positive second derivative means minimum value. So minimum by second derivative test. Do you need to check to see if your critical points are in fact minimums? Or in essence, do we need to do the part that I just put in a box? The answer is, for a multiple choice question, probably not. I mean, it proves that your answer is in fact a minimum, but you don't really need to do that for a multiple choice question. For a fruit response question, you should do this because it is not a whole lot more work. I mean, I did it there in 2 lines. If you'd actually taken the time to plug in the point, you might take 3 lines. It's not a lot more work, but the grader can dock you points for leaving that out. And they would be completely justified in doing that. If they don't dock you points for not doing this, well, you got lucky. You got an easy grader who's, you know, they're not being very harsh on you because you did find the correct dimensions. But a grader that decides to dock you points for leaving this off is absolutely right in doing so, because even though you found the right dimensions, you didn't show that they were the right dimensions without this step right here. Okay, so with that, let's move on to the next question. So the next question is, find the equation of the tangent line to the curve given implicitly by e to the xy equals x squared plus y squared. At the point 0, 1. Okay, so we have here the curve and the point. We just want to find the slope. So, like we did yesterday with this, okay, so e to the xy is something that's probably a little difficult for people to take the derivative of in Calc 1. It's going to end up being e to the xy times y plus x y prime, but we're going to do that slowly just to make sure that we feel comfortable with it. Okay, so we want to break e to the xy into an inside function and an outside function so we can use the chain rule. The outside function is e to the x. The inside function is xy. Do we see how when we plug this xy into that function, we get e to the xy? Yeah, of course we do. It's not so hard. But doing it this way, when we take the derivative, we get e to the x. We get the product rule here gives us y plus x y prime. We plug this into this. We get e to the xy. And then we multiply by this, giving us y plus xy prime. So, exactly what I said it would be. That's the left side of the equation, taking the derivative of it. And then the right side is 2x plus 2y y prime. Now, here's the thing. At this point, we can either solve for y prime and then plug in the point, or we can plug in the point and solve for y prime. Once we've taken a derivative, plugging in a constant doesn't harm our solution. If we plugged in these constants first and tried to take the derivative will treat the x's and y's as constants because you've turned them into constants, and that changes the solution that you get. and specifically, it changes it to the wrong answer. But after taking the derivative, if you're not taking any more derivatives, plugging in your constants doesn't harm anything. So we're just going to plug in x is 0, y is 1. So we get e to the 1, sorry, e to the 0. 1 times 0 is 0. Times 1 plus 0 equals 2 times 0 plus 2 times 1 y prime. So we get just, this is e to the 0 is 1 times 1 is 1 on that side. This is 0. This is, so we get equals 2y prime. So y prime equals 1/2. That is our slope. Here's our point. We're asked for the tangent line, so we just go point slope form. Y minus the y coordinate equals the slope times x minus the x coordinate. And we can simplify this if we want. Y equals 1/2 x plus 1 is in our slope intercept form, although point slope form is perfectly reasonable. Okay, so let us look at the next question. So here we have a boat is pulled into a dock by a rope attached to the bow of the boat and is passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 2 meters a second, what is the rate, at what rate is the angle between the rope and the horizontal increasing when that angle is pi over 6? Okay, so here is the thing. It is completely unrealistic, but we get to assume that this rope is a line, okay? That's not going to be true. The rope is going to sag in the middle of the actual physical problem that's going on here. But we're going to assume that the rope is in fact a line. Part of why we can assume that is because we don't do hyperbolic sines and cosines anymore, which are the actual curves that ropes form when they're hanging between points. So if you ever looked at, say, a telephone wire going between two telephone poles, that's not a parabola. That's actually a hyperbolic cosine curve. But in this problem, we're going to assume that these are lines. So I'm going to draw my diagram here. We have the boat is at this corner of our situation. The dock is up here. And this is a 1 meter between the boat and the dock, the bow of the boat and the dock. And we know that the rope is shrinking at a rate of -2 meters a second. Wow, that is a fast rope. 2 meters a second is amazingly fast. Anyway, so we have 1 meter here. We are told that the angle here is pi over 6. And we want to know at what rate is the angle between the rope and the horizontal increasing. Okay, so what we know is that we're going to call this side length x, and we're going to call this angle theta. Okay, so we know that x over 1, that's the hypotenuse over the opposite, is equal to the, let's see, opposite over hypotenuse is sine, so hypotenuse over opposite is cosecant of theta. This is our relation, so we just get x equals cosecant theta is our relation. And we're going to take the derivative of both sides. So we get dx dt equals negative, derivative of cosecant is negative cosecant theta cotangent theta d theta dt. And the angle that we're given is pi over 6. And dx dt is -2. So -2 equals negative cosecant of pi over 6 times cotangent of pi over 6 d theta dt. We look these values up on our chart. I have, by the way, a trig series of videos. Goes through a bunch of topics related to trigonometry, including reference angles. We look those up, we solve for d theta dt, and that gives us the answer to our problem. I'm not going to bother doing it like that because it's trigonometry and we're worried about calculus right now. So, next question. Find the derivative of arctangent of x to the 3x. So, with this, we have f of x equals arctangent x to the 3x. So, with this, we have a function as our base and a function as our exponent. So we're going to need to use logarithmic differentiation. So taking the log of both sides, we get ln f equals 3x ln arctan of x. The exponent comes down as a coefficient in front of the natural log, using our log simplification rules. Okay. So, from here, we take the derivative of both sides. We get f prime over f. On the left side, we get 3 ln arctangent of x plus 3x arctangent of x times x squared plus 1 in this side. Okay, so what we did here was the product rule. So derivative of the first times the second plus the first times the derivative of the second. And then, to get the derivative of the second, we use the chain rule, which I guess if I did it slower, it would be ln x is our outside function, arctan is our inside function, derivative of ln x is 1 over x, derivative of arctangent is 1 over x squared plus 1. Plug this function into this function, so that's 1 over arctan x, multiplied by this one. That's 1 over x squared plus 1. So this is our derivative. We multiply both sides by f so that we can solve for f prime. F, of course, is just our original function, so we multiply by arctangent of x raised to the 3x power. And this is our derivative. So that's not so bad. It does look pretty cool, though, if you were to show your friends all the calculus that you learned. That would be a problem that would look really cool. Okay, so our next problem, we're going to evaluate a bunch of limits. Okay, so our first limit is going to be the limit as x goes to infinity of 3x squared e to the negative 4x. Okay, so if we plug in infinity, we get infinity times 0, which is indeterminate. So we're going to have to rewrite this in a new form. I'm going to do it this way. 3x squared over e to the 4x. This gives us a infinity over infinity indeterminate form, which L'Hopital's rule will work on. So infinity over infinity means that we can use L'Hopital's rule. We get the limit as x goes to infinity of the derivative of the top, which is 6x, over the derivative of the bottom, which is 4e to the 4x. We plug in infinity, we still get infinity over infinity, so we use L'Hopital's rule again. We get the limit as x goes to infinity of 6, which is the derivative of 6x, over 16e to the 4x. The top is a constant, so its limit is itself. The bottom goes to infinity, so constant over infinity equals 0. 0 is our limit here. Or we could realize that exponentials dominate polynomials. So since the exponential is in the bottom and a polynomial is in the top, the limit will be 0. You can prove that if you have some time to practice that. The next limit, so by prove that, I mean prove that this, whenever you have a polynomial over an exponential, the limit as x goes to infinity will be 0. Okay, so the next one is the limit as x goes to infinity, sorry, as h goes to 0 of a to the 1 plus h minus a over h. Okay, so this here, we can recognize this. This is actually the derivative of f of x equals a to the x at x equals 1. So, the derivative of f of x. That was weird. So, like, if we look at this, we recall that the derivative of a to the x is a to the x ln a. Then we just plug in 1, we get a ln a. This is what our derivative is going to be. Like we can tell that by recognizing this is the definition of derivative. However, we're going to need to do this. So, if you wrote out, I recognize that this is a limit that is a derivative, and here's the derivative rule, that should be a fair way to answer the problem, because at the end of the class you have all of your tools, and it didn't explicitly say you couldn't use the fact that you recognize a certain limit as a derivative. However, if you don't recognize this as a derivative, then what you can do is you can factor out the a from the top. You get a times the limit as h goes to 0 of a to the h minus 1 over h. Do we need to do that? We probably don't need to factor the a out. We could probably just use L'Hopital's rule. Now, yeah, we could just use L'Hopital's rule. That would work. So, but I already factored the a out. So what we get here is this goes to 1, that's a 1, 1 minus 1 is 0, this goes to 0, 0 over 0 is an indeterminate form, so we can use L'Hopital's rule. That's going to be the limit as h goes to 0 of a to the h ln a minus 0 over 1. As h goes to 0, a to the h goes to 1. 1 times ln a is ln a. And then we multiply by this a. A ln a is our answer. Okay. We have... Okay, so continuing on. Oops. Let us look at our next question. By the way, the live stream is going on for 12 more minutes, and then I'm going to end for today. If you have questions, please put them in chat. I guess if you've emailed me questions, I can pull those up too. Okay, so we will continue on with the problems in the order that they are in the packet I emailed all of you. So the next question is, write the limit as n goes to infinity of the sum from I equals 1 to n of e to the I over n times 1 over n as a definite integral and calculate it. Okay. Do this using the fundamental theorem of calculus. Let me write out this limit. N goes to infinity of sum from I equals 1 to n of e to the I over n times 1 over n. Okay, so what we really need to know this is we need to know a and b and f of x. Okay, remember, we have the integral from a to b of f of x dx equals the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I times delta x, where delta x equals b minus a over n, and x sub I equals a plus I delta x. So this is the definition of the integral. This is what we're trying to reverse engineer. Basically, this here is what we get after we do these calculations. Or we're trying to go backwards. Do these calculations backwards to run and get back this. This is what we're looking for. So the first thing that we do is we say, we want to try and find an f of x sub I and a delta x. So here is, it wouldn't do that. Here is our f of x, and here is our delta x, we think. So delta x equals 1 over n, meaning that b minus a equals 1 is what we get. Now, when we look here, we get I over n, which is what, so a plus, sorry, that's not a plus, I b minus a over n. This is what delta, or x sub I should equal. So looking at this, this looks like f of x sub I. The inside of this is I over n. So that makes me think a equals 0. So 0 plugged in. And then I times 1 over n. I times 1 over n. So that means b is 1. So what we get when we put all of this together is it looks like our integral should be the integral from 0 to 1 of e to the x dx. Okay? It's a little messy, but basically, first thing to do is you want to try and split whatever is inside the summand, or the summation, into a function and a constant over n. The constant represents the distance between a and b, and then you try and look at f and split it into the outside function f and the inside function x sub I. X sub I will always be of the form some constant, in this case our constant was 0, plus some constant times I divided by n. So the constant was 0 plus I times another constant, which was 1 over n. That gave us our I delta x and our a. We already knew that b minus a is 1, so a plus 1 was 1. That gave us our resulting integral here. Okay, so from this, we find an antiderivative. Well, the antiderivative of e to the x is e to the x. We evaluate at 1 and 0, so we get e to the 1, plugging in our top endpoint, subtract off e to the 0, which is our bottom endpoint, and then ends up being e minus 1. This is that limit. Okay. So the tricky parts are you have to have your definitions memorized, and then you have to be patient enough to try and break apart from the limit what the different pieces of your definition are going to be. Now, this problem, maybe not with e to the x as a function, but going backwards from a Riemann sum to an integral is always on the final. Usually 1 or 2 times. Probably not 3 times, but at least 1 or 2 times this type of a problem will show up on the final. So please make sure you feel comfortable with this type of a problem. Okay, so going on to our next question. Use the definition of derivative to find f prime when f of x equals the square root of x. So f of x equals the square root of x. F prime of x equals the limit as h goes to 0 of f of x plus h. That's going to be square root x plus h minus f of x, that's square root x, over h. With this problem, the way that we do this is we have to multiply by the conjugate over itself. So, put little braces around that. Square root x plus h plus square root x over itself. Square root x plus h plus square root x. How did I know to do this? Well, I guess the first thing that I noticed is if I plug in 0, I get square root x minus square root x is 0 on the top, and I get 0 on the bottom. It's indeterminate. It means you have to do some sort of manipulation. Also, when you're using the definition of derivative, you cannot do derivatives to find the answer. Okay? It's circular logic. Okay? You're not allowed to use the definition of derivative is used to find derivatives. So you can't use the derivative to you can't use derivative rules to prove something with the definition of derivative. It's circular logic there. Okay, so we're going to multiply by the conjugate over itself. The reason we're doing this is since we have these square roots and we need to get rid of the square roots, multiplying by conjugate, which is just what you get when you flip this sign. If you had a plus here, you do a minus here. If you have a minus here, you do a plus here. Flipping that sign gives you something called the conjugate, and it's a great way to kill off square roots. So we do this, we get f prime of x is equal to the limit as h goes to 0 of h times square root x plus h plus square root x on the denominator. I didn't leave much room for a numerator. And then on the top, we get a lot of nice cancellation because this is a difference of squares. So we're going to get x plus h minus x on the top. This x cancels with that x. This h cancels with this h. And we end up with the limit as h goes to 0 of 1 over square root x plus h plus square root x. Now, h will go to 0, and that leaves a square root x plus a square root x on the bottom. Those add together, so we get 1 over 2 square root x. I would recommend, whenever doing a definition of derivative problem, this is the end of the semester, you know your derivative rules. Check your answer using your derivative rules. So this original function is x to the 1/2. The power rule says that f prime of x equals the power. You take the power down as a coefficient. You subtract 1 from the power, like so. Hey, look, 1 over 2 square root x, which is exactly what we got using the definition. So that's how to check your answer. You have to do it the long way because they specifically asked definition of derivative, which means that you're not allowed to take any of your derivative rules. You have to go back all the way to the limit definition and do it that way. Do limit definition questions show up on finals? Well, they did on this one. So they're fair game questions. And they're actually not so bad to do, to be honest. There are way worse questions we could ask. Kind of like that 5th degree polynomial question we asked in yesterday's live stream. That's a terrible question. I would not put that question on an exam. Just because it's way too much algebra, not enough calculus. This is a calculus class. Anyway, so the next one is show that the natural log of x plus x minus 2 equals 0 has exactly one real root in the interval 1 to e. So ln x plus x minus 2 equals 0, interval 1 e. Actually, it gave us open brackets there, so let's do that. 1e. So here's our problem. We want to show that this has exactly one root, so let's let f of x equal ln x plus x minus 2. F is continuous everywhere. It is defined. So well, next part. It's continuous everywhere it's defined. And we know that f of 1 equals ln 1 plus 1 minus 2 equals 0 plus 1 minus 2, which is negative 1, less than 0. F of e equals ln e plus e minus 2, which equals 1 plus e minus 2, which equals e minus 1. We know that e is about 3, a little bit less than 3. So in particular, this is greater than 0. So f has a root by the intermediate value theorem. This is part 1. Part 2. Part 2 is going to show that f of x has no more than one root. Okay? We're going to do this by proof by contradiction. So suppose f of a equals f of b equals 0. And a, b are in the interval 1 to e. Then, since f is continuous and differentiable on 1 to e, Rolle's theorem implies there's a c between 1 and e such that f prime of c equals 1. So, well, we look up what f prime would be. We calculate out, since f is ln x plus x minus 2, f prime of x equals 1 over x plus 1. Derivative of natural log is 1 over x. Derivative of x is 1. Derivative of negative 2 is 0. So we get 0 equals 1 over c plus 1. So 1 over c equals negative 1. So c equals negative 1. But c is between 1 and e. Contradiction. We said that c is between 1 and e by Rolle's theorem. But the only c that actually works is negative 1, which is not between 1 and e. Negative 1 is not negative 1 is not positive. And only positive numbers exist between 1 and e, so c isn't there. Okay, so we get our contradiction. Proof by contradiction works by first we make an assumption. Our assumption was 2 roots. So our assumption is 2 roots. This is our assumption. Proof by contradiction says we make an assumption. We find out that there's a contradiction. And because there's a contradiction, it means that our assumption was false. Well, our assumption was 2 roots that are different from each other. That's false, meaning that there cannot be 2 different roots. They have to be the same root. Okay, so that's our conclusion of our theorem. We get there is exactly 1 root. Because the first part showed there is a root. The second part showed there can't be 2 or more roots. Conclusion, there is exactly 1 root. And that is a nice place to end the video for tonight. I will try and have 2 videos tomorrow. One will be sometime in the morning or maybe early afternoon, and then the other one is going to be, let's see, tomorrow is Thursday. Ooh, tomorrow's Thursday. Guess the other one is gonna also probably have to be in the afternoon. So we're gonna do 2 videos tomorrow. If you have questions, send them to my email between now and then, and we will get to them. And of course, during the live streams, put your questions in the chat. See you tomorrow. Good luck on the final. Bye.